It's fine. Please start.
Okay. Yeah, sorry, my audio keeps dropping out on this side. So I think I'm all right, though. So I am Chris Wilkinson. I am the Director of Planning and Architecture of Internet 2, as mentioned. And I'm going to talk today a little bit about our NGI next generation infrastructure effort that we just completed on our domestic network, and extend a little bit into how that applies to our international exchange points and our international connectivity as well. So the goal is to kind of make a quick run through that program, talk about what we did and what we achieved, and then move quickly onto how we're going to apply what we learned onto our exchange points and connectivity. So just for a quick recap, because I think it's always useful, Internet 2 is a backbone for research infrastructure in the United States. We have a large number of regional and global partners, and we have a fabric that connects those partners to the cloud and each other. We also provide working models for collaboration domestically through our community, as well as software tools that enable interaction with both the core network and the cloud resources and international resources throughout. So little big science, large and small projects, and a lot of different things in between. We have four main effort areas. There's the network itself, which I, of course, spend most of my time on. We have a large security effort as well, including trust and identity, and roaming Wi-Fi, access to cloud infrastructure as well, and then community organizing, of course, as well. So Internet 2 has sort of many different functional areas. Of course, I'm going to talk chiefly about network tonight and this morning. Just a few quick stats of the network. I'm not going to read through them, but lots of institutions, lots of countries. We have a very large membership domestically. We extend into industry and government as well. And we have a lot of folks who consume the services on the platform. Now, talking a little bit about the Next Generation Infrastructure Program, we just wrapped this up. And it was really intended to be a full stack look at not just the network, but also the services provided by the network, centered around 5 use cases: data-intensive research, enhanced cloud access, software-driven infrastructure, sustainable economics, and infrastructure sharing. So each of those have a variety of use cases associated with them, but these were all driven out by our community through that process. We also did a complete greenfield network, meaning we built from the fiber up through the software stack. That doesn't mean that we replaced every piece of fiber or every piece of software. That's certainly not true. But we did go through the entire stack and try to make improvements everywhere we could with the funding and the staff that we had on hand. Of course, traffic is ever growing. These are total petabytes carried, petabytes per month. Each of these bins is the months of the year: January, February, March, and so on. Over time, there's continuous growth in every single month. Shown on this graph, there is one dip that's not surprising around the early stages of COVID. But since then, traffic patterns have largely returned, and we are seeing effectively exponential growth on our services. Maybe a little bit less, but right around that as expected. NGI has been a long process. We started way back in 2016. I'm not going to read through each of these, but basically the origin of the project was 2016 and the end was 2022. Arguably, we're still doing some cleanup right now, although the last of the legacy gear is out of the network. Our old network was 100 gig based. Our new network is 400. Lots of new fiber, completely new packet platform, all came into fruition over the course of 6 years from inception through completion. Obviously, a very big effort. So going through each part of the stack that NGI, we replaced our eLeaf, which was primarily intended for dispersion compensated systems with SMF-28, much better for coherent transmission. We installed a new ROADM system nationwide, which is capable of FlexGrid, channels larger than 50 gigahertz. That system is still EDFA based. It's not Raman or Raman, depending on how you pronounce it. It's simple EDFA amplification, but it's all been optimized and cleaned throughout for the best signal to noise ratio. Footprint got expanded in many locations, built into all of our cloud locations, diverse fiber into all of our international exchange points. And we ended up with 75 ROADM sites, over 271 ILAs across the nationwide footprint, and 86 spans. So overlaid on that, we built with Sienna Waveserver 5s, which are capable of running at 400 to 800 gig line rates and delivering clients at 100 or 400 gig. On top of that is a Cisco 8201, 8202 based switching platform, which consists of 77 routers distributed across 47 sites. Those routers are built in a mesh topology, meaning 2 routers at a large site are connected independently to 2 routers at an adjacent site. So there's a lot of both capacity and every location has multiple links on multiple Waveserver modules using multiple routers. There are some small sites in the network where there's only a single router, but those typically have a connector that has other connectivity to the network, one of our members elsewhere. We use Cisco NSO from basically bare metal up through a fully functional router. The NSO system overlays the base config and then starts to build the IGP up through the higher order services, layer 2 and layer 3 VPNs on those Cisco 8201s. It provisions effectively all the services and all the route policy for every node on the network. And if manual configuration takes place, it flags that and lets us know as well. So very top to bottom system that ensures that the network remains as consistent as possible across the entire platform. With 77 routers, it's very important. We designed a whole new route policy for those routers since we were on Juniper. We had to transition over to the Cisco route policy language. That meant every single policy facing both one of our members, as well as our peers, our commercial peers, as well as all international peers had to be rewritten and translated. So we took that opportunity to make a lot of optimizations to our platform and the route policy language to provide as much flexibility in the configurations and consistency as possible across the deployed services. Last, and because so many services are cloud important, and I mentioned this a little before, we did add redundant resilient routers to all of our cloud locations. So every location where we pick up Microsoft or Amazon or Google or any redundant cloud peer, we have 2 routers that they can connect to at the local site that are connected redundantly back to redundant routers on the core network. All routers are effectively the same from a configuration standpoint, but because of making sure that we meet the cloud resiliency requirements, all cloud locations have this diverse router configuration. So by going to a smaller device consistently across the network, we were able to add more devices into the platform. This is what it looks like. It's extremely compact at every location. This is New York, actually, which is one of our largest sites. And effectively, it's 2 half racks worth of equipment. You've got the Sienna 6500 and Waveserver platforms on the left. You've got the Secure Management Network and Cisco 8200s on the right. Not shown in this particular diagram that was added later was the Man-LAN exchange point, which consists of 2 QFX switches. They were mounted below the 8201s. And it all effectively fits into 2 racks with very low power profile. Just some quick stats. Our network in 2010, consumed 300,000 watts of power. Our NGI network with all of its components consumes about 100,000 watts of power. So that's a decrease of a third, as well as another probably quarter of the overall footprint. I need to put square footage in here as well. So much smaller platform, much lower power utilization, and that was definitely one of the goals for making a sustainable network. As mentioned, NSO was heavily leveraged for the service deployments. We used it for BGP. All tooling and validation through the transition was handled by NSO, and that config control was closely monitored. So automation heavily played a role in this. We also are working on our Insight console, which manages the platform. In the past, we had multiple interfaces, which one went to view services, provision new services, look at service status. And our goal is to merge all this together into a single console, and this will extend into the international exchange points as well. So applying these technologies, and I'm being a little mindful of time, I think I have about 5 more minutes. We are beginning to roll out the same technologies that we saw in our domestic footprint into our international connectivity. So one of our big efforts right now is to bring up 400 gigs across the Atlantic. We're doing this in partnership with Canary and ESNet. We've acquired capacity on the Amity cable, 1x400 for Internet 2 and Canary, and then 2x400 for ESNet. That's due in mid-2023. Interestingly, it will require us, because of the cable landing, to build out an exchange point in Boston and add that to our overall platform design. So in addition to moving the link to 400, we will also be pushed towards having our first 400 gig exchange point. And of course, the goal is always to have multiple redundant links. And so we're exploring possibilities for a second link into New York or Washington across the Atlantic as well. This is due in 2023 due to construction. As part of this, we're talking about upgrading our exchange points themselves. Right now, those are based on Juniper QFX switches, which are limited to 100 gig. We're working on a design for 400 gig exchange points using either a Cisco 8200 platform or a Juniper PTX 10001. Those we haven't decided yet on which of those we're going to go with, mostly because we are doing price analysis and lead time analysis. I'm sure others have experienced that we are seeing lead times of anywhere from 8 months to 12 months, even upwards of 14 in a few cases. So, switch selection is dependent some on that. But we're pretty confident that we'll be able to meet the Q2 of 23 goal for the cable delivery across the Atlantic. We're also working on bringing up 400 gig connectivity between our exchange points. Here I've got all 3 shown: Boston, New York, and Washington, D.C. Our goal is to not only have a linear path between them, but also have an alternate path around, so that traffic that's transiting through the exchange points has as much bandwidth as possible, both between the exchange points and our core. We also had a pilot program with Pacific Wave that had dedicated links crossing the United States. And the original links were from New York to Seattle and New York to Los Angeles. We're working on an upgrade plan for those as well. We had merged those links temporarily into the core network, and we need to bring them back online. But those dedicated links are key to providing an administrative domain to optimize things like NSI and AutoGoal for transit traffic that's going through the United States. And the original AP-REX consortium had a specific scope, but I think we're hoping to expand that even further in the coming years as we talk with folks in the US. We are planning to roll out the same automation and protocol layers into the exchange points that we deployed onto the core. Things like EVPN with the XLAN and SRMPLS for intranode connectivity. I mentioned NSI previously. We very much want to provide good support to the Fabric and the other communities using AutoGoal and Sense. So we're working on ways to extend that. We already have some of that in Manlan and Wix, and we want to continue that development work. Currently, the exchange points are configured through OESS, our legacy provisioning system, good platform, but as we move more towards NSO and NS Console, we would like to integrate the exchange points fully so that the exchange points have that same consistency and manageability, as well as having service models that are consistent with the rest of the platform and specialized to the global exchange points. And then lastly, integrating that more as we move away from OESS into NS Consoles so that those services can have good monitoring, automated provisioning, and then hopefully we can expand our support of pushing data out to our community partners from the exchange points. I've had some limitations there that I'm hoping we'll be able to move through in the next year or so. Last slide, we are also working on DTNs domestically. We are running a pilot node out to Amsterdam. These are part of a cyber infrastructure program. We currently host 5 of them. We're adding 5 more domestically. There's many more institutionally through the National Research Program. And then we're hoping to do we have a pilot node that we've been planning to put out in Amsterdam. And if we're successful at doing that, we may be looking for other partners as well. These are data cache and storage systems that are used by researchers for distributing data. So that, I think, is about all we have. Of course, for those who can travel, I have to give a nod to our first in-person meeting that'll be in December in Denver. And hopefully I'll see some of you folks there. So happy to take any questions via chat or audio and or after the program.
Thank you very much, Chris. Now we are open for the question. So do you have any question? Please type or unmute your mic. Okay, from the chair, so that I have a question. So how much utilization of 400 gigabps in your network currently?
I only had room for so many slides. It's a good question. So we've seen upwards of 150 gigs on a city-to-city pair. So we, our primary bandwidth route from east to west runs from Washington to Los Angeles. And we've seen 150 to 200 gigabits per second, 95th percentile on some of those links.
I see. So the over 100 gigabps is very good here.
It was just in time.
Yeah. So, and other question. So this is a sensitive question, but how many telecom carriers do you lease in order to make this infrastructure for the purpose of resiliency or something?
So I think if I heard the question, you were asking how many leases we have basically on the platform.
Yeah.
Yeah. So Lumen, otherwise known as CenturyLink, is our primary fiber provider. And so probably about 80% of our platform is on a single provider network. Some sections of the network where there was not fiber availability, we do have other partners that we lease from. So I would say there are 3 fiber providers or 4 that we lease from. And then there are probably about 18 co-location providers that we lease from. Many of them are Lumen, but we also site with our community in some places. We use Equinix and a bunch of other folks as well.
Okay, thank you. It's very tough work. Thank you for sharing the information. Question comes from Konishi-san. Could you speak?
Or I see the I see the question, and yes, absolutely. Prior to COVID and prior to our NGI program, we had an extensive collaboration with Pacific Wave, and we are actually in the process of restarting that. We had a pilot program called APREX, where we worked together to integrate the East and West exchange points. And we, of course, were really hoping to bring in our other domestic partners as well on that. I'm probably, it may be a little improper for me to say, but that's the hope. And so, yes, absolutely. We do work extensively with Pacific Wave, and we'll continue to do more and more as time goes on.
Thank you very much.
Thank you for the question.
We can have one more question. Do you have any question, audience? Okay, thank you, Chris, for informative presentation.
Thank you.
Okay, let's move to the next presentation. The next speaker is Jennifer Schopf, International Networks Director, Engagement and Performance Operator Center at Indiana University. Welcome, Jennifer.
Thank you very much, and I appreciate the opportunity to talk today about what's happening with the TransPAC program. TransPAC is part of a larger portfolio that's international networks at Indiana University, which includes both the TransPAC links and the near links to Europe, as well as some domestic programs. Both of those are shown here. So of course, these are all NSF, US National Science Foundation funded circuits. They also fund circuits and network services in the Asia Pacific through PIREN, exchange points through PACWave and AMPATH and AMLIGHT in Florida, and links to South America and Africa through that program. As part of our portfolio, of course, we've got TransPAC, which supports 200 gig links, labeled here A and B, Tokyo to Seattle, and part of the consortium between Singapore and Guam. This map shows you which countries were endpoints for data transfers in 2021. So for TransPAC only, that was over 124 of 195 countries shared at least 10 megabits of data over the course of the year, which is pretty much everywhere that has a functioning R&E network that would be appropriate to talk over the Pacific links. TransPAC supports the TransPAC PACWave 100 gig Seattle Tokyo circuit. That's been around for 7-8 years now, joint with PACWave. Jonah was on the meeting last night. I believe he was planning to come again today. That's been a very nice collaboration, and that link has been very stable and up, and the workhorse for this collaboration. Joint with Chris and Internet 2, Singaren, and ArenaPAC. We're also part of the Guam Singapore Circuit Consortium that's been up and running since January. I say sort of running because it came up in January briefly, and then it went down again. It came up in February, March. We've had some reliability challenges with that in the South Pacific, and that's currently being investigated to try to figure out what's going to make sense there. Part of why we liked that circuit was for the redundancy of routes. So TransPAC, of course, is a member of the Asia Pacific Oceania Network Consortium, along with Internet 2 and 8 or 9 other partners, as shown here. This Guam Singapore Consortium down here was on a different path than many of the other Northern Pacific links. And so it gave us this redundancy and resilience, which we really need in the realm in order to have reliable communication for our science projects. Each of these links shown here is a 100 gig or high-speed network connection. And it's really, this group grew out of the APR collaboration, which was basically a figure-8 plus an extra loop on it. You can see how much more complex this network topology is. I'm really quite pleased and proud of how all of these teams have been brought together. And this isn't just an MOU that's a piece of paper. We had an hour-and-a-half session yesterday talking about the collaboration in a panel of speakers addressing everything from how we're putting in place backups to support for experiments to other application work. So it's been a really successful way of growing the community in this space and looking at these networks as a way to support more than just basic connectivity and you know, is my circuit up today? However, the question of is my circuit up to date, of course, is the fundamental one. For the APOnet collaboration and for TransPAC specifically, we use NetSage to monitor this. If you go to http://aponet.netsage.global, you will see this page, which is the screenshot from about 3 hours ago when I was putting together my talk slides. This isn't all of the APOnet links, but it's most of them and it's growing. We're hoping to get the rest of the SNMP data for the links online before supercomputing, so before early November. If you go to that webpage, you can hover over these links and see exactly how much each of these is transporting and some other details about them. You can see over the last what does it say? Last 30 days, 31 petabytes of data has been transferred across these links, across all of them together, which I think is really quite impressive. Another way to look at that is how much data have these carried, looking at a 3-month time frame, so a 90-day time frame, which is more useful in many cases. We've had data over those links from 5,600 source organizations, almost 9,600 destination organizations, you know, thousands of ASNs, and a wide variety of countries. The countries here are counted slightly different than the ones that I had. For example, Guam counts as its own country in this count, whereas we all know it's actually part of the US. But there are a number of different NetSage pages that you can look at and see how these different data flows are taking place over time. One of the really interesting things for the links that we have flow data for, which is not quite all of them at this point, is you can look at top talkers data. And this is really useful to because we can understand who's using the links and why, and how we can help those collaborations get better data transfer rates. Because as Chris was talking about, just now, you know, he got the question of, well, what's the speed that you're seeing between two city pairs? Looking at that, you can understand what the application use is and make sure that they're getting that done effectively and efficiently. So for example, A-Star, as many of you have heard Francis talk about, has their big data collector site. So we see them talking to a number of sites, both as a source and a destination. You know, NetSage shows us this data, and I'm going to zoom in, you know, so I was fascinated here. We see ARNet is a top pair with the Science Engineering Institutes, which is actually part of the Singapore Science Complex. On NetSage, you can dive in and see, well, this is actually, it's 8 petabytes of data in one direction. In the other direction, it's about 7 terabytes. Sharing between these two sites. The fascinating thing for me, though, is it's 104 megabit per second. Shouldn't be 104 megabit per second looking at the ARNet links and the Singaran links. So this is something to look into and figure out, okay, well, why exactly are we shifting 8 petabytes of data and having it take that long? And if you actually zoom in on this page, you can see it took 24 hours to transfer that data. That shouldn't be happening, right? So maybe we could look at this and find out more detail. I believe this is actually the same experiment that Francis spoke about yesterday in the APOnet section, the Gatti supercomputer in Australia sharing data with Aspire 2A in Singapore. He's seeing much higher transfer rates in this, but we're seeing lower ones, and that would be worth talking about how to do this and what's actually going on and what's the scientist experiencing. Because keep in mind, we're not putting the networks in place just to be able to draw pretty lines on a map and say, hey, mine is bigger, right? We're doing the networks so that we can help researchers and scientists share their data and collaborate better. So what should we be seeing between these sites? You know, most US Asia flights are only achieving tens of megabits, if that. So the problem here is not the backbone. It's not TransPAC, it's the connections outside of TransPAC. How can we work together to resolve these issues? And this is still something that we actively try to do. Every month, we spend time with other collaborators looking at science collaborations and looking at these end-to-end transfer points. So for example, here's some work we did with CCNY and QTech Institute for their Cosmos project. This is a mobile wireless testbed. They were working between the two institutions using some really crazy tunneling technology. They had a large packet loss and only 8 megabit per second throughput that was very asymmetric. We worked with them on this. We resolved where the packet loss was coming from and got a 10-fold increase. Another example, I'm sure you've all heard of the ALMA experiment. That's in northern Chile, but they're sharing data with a number of different sites. One of them in particular is at WIDE and part of NAOJ. So that data flows in part over one of the TransPAC links. We're seeing the data there. The performance wasn't great. We narrowed the problem down to a wide arena pack switch that needed to get upgraded to 100 gigabit. We're looking at DTN replacements. Again, you heard about the supply chain. We're all running into that. But there are things that when you look at who is sharing large volumes of data, you can adjust what you're doing on your sites to try to accommodate for that. We're not going to see this if we just look at uptimes. We're not going to see this if we just look at vanilla volumes. So I think we really need to be thinking about how do we better support research, understanding who's using the network, using tools like NetSage or whatever your favorite flow data discriminator is, working together to improve these slow rates of transfers, looking at data transfer patterns so we can see what's happening. You know, in part, we worked extensively with Francis's group in Singapore because they pull in data from a number of different sites. And even if things are going great on their end, when they pull COVID data sets out of the National Library of Medicine, and it takes a really long time, this impacts our science, which impacts our, the general state of the world these days, right? This isn't novel. So open invitation to anyone here. My team looks at these data sources across all of the different APOnet links. We'd be happy to work with you if you know of instances where things are not transferring as you might hope, and we can try to speed them up. This goes back to what we've always said, TransPAC, it's more than just a network. We do science support for applications. We do testbed support for things like Fab and Fabric. I wanted to speak briefly about experiment support because now that we've gotten to August, we're less than 90 days away from supercomputing this fall, where there are tens of experiments running. We heard a lot yesterday, and I'm sure we'll hear more about some of the NICT experiments. This is one where it shows that they've got 5 different possible 100 gig paths for their experiments going to SC22. That's really great. Part of what's allowed us to do this is we can shift all of the production traffic on all of those links to a single path, clearing the bandwidth for an experiment to have a full circuit to experiment on, which is unusual. This is something we do for supercomputing, but we can do it other times of year with the APOnet support we've got in place now if people are interested, not just for supercomputing or HPC Asia, or the data challenge in 2023. TransPAC does a lot of work also looking at how flows are routed. We all know that data flows can take crazy routes if we just use vanilla BGP. When a link goes down, when it recovers, things don't always bounce back into place. When new capacity becomes available, things shift. We had an instance where the top talker over TransPAC was a China to Hong Kong route that went through Tokyo and Seattle between China and Hong Kong. It took over 3 months to resolve this. Terabytes and terabytes of data going between China and Hong Kong over the ocean and back. Shouldn't have to happen. So we're trying to figure out how we can do this better. Brenna Mead, who oversees the APAN routing working group, is going to be leading a session on this tomorrow at the same time, so 9 a.m. local time for the meeting. I highly encourage everyone who is interested in trying to figure out how to resolve some of these crazy routes to take part in that. So just to summarize, most of you have heard these main points before from me. I'll say them again. TransPAC and the APOnet IU portfolio, we really look at more than just a network. We're not putting in place the circuits just to have them up. We're putting in place the circuits to understand the traffic and the science and to help that be more effective. We're trying to have better routes for data transfers, better performance for data transfers, and better support of the science. If you'd like more information, here is my contact. And with that, this is my last slide. So I will take any questions as makes sense.
Okay, Jennifer, thank you very much for your informative presentation, and also appreciate the arrangement of increase of usability in Asia Pacific Oceania. Do you have any question to audience? Okay, I have a question. So the half years ago, you show the top something traffic information. In that case, most destination was Microsoft, but currently, so the top is APOnet to not Microsoft, but Institute. So what is the most reason why such kind of information science traffic is improved, science traffic is increased?
So the data transfers, who's the top talker for any given period of time will change over time with who's doing what kind of science. So that APOnet to Singapore transfers, 6 months ago, they weren't doing that science. So those transfers weren't there. The Microsoft traffic is mostly that's just irritating because that's people using cloud resources that aren't local. That's people in the Asia Pacific region using cloud resources that are based in the US because someone hasn't configured something correctly that it isn't using a local cloud when it can. Most of the cloud transfer work is completely out of our hands in terms of fixing or correcting. If people don't have, if an institution doesn't have their configuration set up right, so their data sets wind up in the cloud, on the one hand, it's everywhere. On the other hand, it's nowhere. The cloud is simply somebody else's computer. And if you don't have it set up correctly to have that be a computer close to you, then it's not going to be close to you. So, that's in some ways, and it's also, we wind up in a lot of challenges with researchers who are trying to work with the cloud. So for example, about a year ago, we had worked very closely with an astronomy experiment in Puerto Rico where they were trying to upload 50 years of astronomy data. And their first thought was, well, we'll put it in the cloud. It was going to take 43 years for them to upload 3 petabytes of data to the cloud. I'm not making this up. This is what the transfer speed was. And then it was going to cost hundreds of thousands of dollars for any astronomer to ever access it. So we actually actively discourage researchers from putting data in the cloud. There are almost always better approaches that could be done there.
I see.
I don't know if I answered your question or not. I kind of
clearly. Yeah. Thank you very much.
Any other questions?
Do you have any question? It's fine to unmute.
Okay, well, thank you very much. I appreciate the opportunity.
Yes, thank you very much. So that monitoring information sharing is very informative to us. So that please continue, and we are happy to get such kind of information in future. Thank you very much, Jennifer. Okay, let's move to the next presentation. Presenter is Osamu Akashi, Project Professor of National Institute of Information. He provides a SciNet update.
Okay, thank you, Harai-san. Let me share the file.
It's fine.
It's fine. Okay. Can you
yes.
see it? Yeah, thank you. Hi, everyone. I'm Osamu Akashi of NII. I would like to talk about the SciNet update. And let me first introduce the new SciNet logo. SciNet 6 started, and so we can use this SciNet 6 logo instead of SciNet 5 logo. So this logo was determined through the voting among SciNet team members. So this report is about we have finished the migration from SciNet 5 to SciNet 6, and SciNet 6 started from April 2022. So first, I would like to introduce the SciNet briefly. So SciNet is an ultra-high-speed academic network and is dedicated to enhancing the research and education networks in Japanese organizations. So as you can see, SciNet Connect is about 100,000. SciNet Connect 1,000 about 1,000 organizations in Japan, and it also connects the large experimental facilities such as BEL2 or LSC or ITER, and it also connects the supercomputing facilities. I will explain about the HPCI in this presentation. It also connects the research data platform or other facilities. Sorry, no change. Oops. Okay. This shows the transition from SciNet 5 to SciNet 6. SciNet 6 SciNet 6 have applied the 400 gig technologies nationwide and increased the SciNet node and converged fixed and mobile capabilities, enhanced VPN security services, and strengthened the global connectivities. So as I reported in the previous workshops, we are constructing the SciNet 6 in the domestic topologies. So SciNet 6 have covered the all prefectures about using the 400 gig technologies. And also SciNet 6 have placed 70 SciNet nodes in order to improve the accessibility. So this construction has been completed. And as shown in these maps, we have constructed the topologies by connecting the all 70 data center in SciNet. This chart shows the migration schedules performed in the last February and March. This number shows the number of access lines to be migrated on days in February and March. Migration means we must migrate the access lines of SciNet connected organizations from SciNet 5 facilities to SciNet 6 facilities. So the important requirement is we have to minimize the impact of the service suspension time, 30 minutes maximum. So migration were performed in the midnight or Saturday or Sunday. So as you can see, we started the migration in early February. So this schedule is very heavily delayed due to the router delivery delay. So, and the hard deadline is end of the March. So as you can see, we use the last day before the hard deadline to migrate the all access lines. So we can hope successfully migrated the all access lines, but it was, as you can see, heavily loaded work on tight schedule management. So this is hard work for the SciNet teams. So this is international line and collaboration status. As we are participating the APOnet and AR, and we are now preparing the next MOU for ANA collaborations. This is SciNet 6 international lines. So SciNet 6 increase the bandwidth as far as Asia, as reported in the yesterday's APOnet meetings. We added the new Tokyo Guam lines in addition to the existing Tokyo Singapore lines. As far as the United States, we increase the bandwidth line between Tokyo and Los Angeles and New York. In more detail, we also we finished the router installation in New York in the Singapore last June, and unfortunately, router installation in Guam was scheduled last June, but the router installation is postponed due to the GNC problems. But we are currently scheduling the new installation program. We hope this repeat installation is performed in the near future. This shows the APOnet topologies. So previously in the SciNet 5, we implemented the Japan to Singapore line and Japan to Los Angeles lines. So after the SciNet 6, we also add this Japan Tokyo to Guam line and Tokyo to Los Angeles lines with 200 gig line facilities. This is a service of higher service availability for universities. So it means the line multiplexes access to the SciNet. These functions were explained in the previous workshops. So currently, we are started the service in SciNet 6. Also, this is a DDoS mitigation service. It was also explained in the previous workshops. We are now test for actual use, such as the feasibility of the user portal site. So this DDoS mitigation aims to provide more prompt mitigation service. In the SciNet 5, this mitigation service was using the BGP flow specs, and it needs several hours to activate the DDoS mitigation system. And next SciNet 6 facilities, we aim to provide more prompt mitigation service. So I would like to explain about the new topics about the SciNet 6. One is manners. We participated in manners. So we are implementing the manners actions such as prevention of propagation of incorrect routing. It means the IRR registration, and also facilitate global operational communication and cooperations, and also facilitate the validation of routing information. It means autonomous object was registered. So another topic is high performance computing infrastructures using the SciNet. SciNet connect supercomputer Fugaku using the several 400 gig lines currently, and other members are connected using the 100 gig or more bandwidth. SciNet connects these organizations using the SciNet 6 facilities now. And the final other topic is experiment of remote operation of surgical robot system using SciNet. Remote operation of a surgical robot system is expected to improve the local medical circumstances. And the Japan Surgical Society have been verifying the capability of this system between university hospital. As you can see, in this experiment, Hokkaido University Hospital and Kyushu University Hospital used this two hospital away distance of these two hospital is about more than 2,000 kilometers, and the round trip time is about 30 milliseconds. So in this experiment, we change the bandwidth using the L2 VPN systems on SciNet. So as you can see the below down graph, so we change the bandwidth, and at the decreasing this bandwidth, image of used for surgical system are degraded. So in this system, in this experiment, sergeant cockpit and between the sergeant cockpit and real operational system were very critical, but depending on the changing of bandwidth, disruption occurred, and we can test the safe bandwidth using this network experiment. Okay, this is a summary of the schedule. We have finished the migration from SciNet 5 to SciNet 6, and SciNet 6 started its full-scale operation in April 2022. So we are now doing the adjustment work and modification of functions. And in addition to that, we are now preparing the next Japan-EU international lines. Procurement is, we are now preparing the procurement, but the world situation is very difficult. But we will prepare the next EU-JP line. Thank you for attention. Thank you.
Thank you, Akashi-san. Now, I am very happy to hear that the SciNet 6 migration was successful in the March of this year. Yeah.
Thank you.
The presentation is, this session is open for the question. So that, do you have, audience, do you have any questions? Any question? I have a question. So from this April, so do you found some change of traffic characteristic from 100 gigabps network to upgraded for 100 gigabps?
Oh, actually, we are not have detailed analysis, but some point we observe the lot of traffic between large experimental organizations. So we think the 400 gig facility is used using the large bandwidth.
Okay, thank you. The example is the remote robot surgery in the last slide.
It isn't.
So this is the last year's experiment, but after the migration, so such kind of experiment will be continued.
So yes, we are now next phase of we are preparing the next phase of the experiment. But in the previous experiment, we lowering the bandwidth, so it is not use the SciNet 6 capability fully. So maybe SciNet 6 full capability is enough for experiment or using the surgical systems, but it is aimed to real applying the real network system, such as a commercial network or so on. So SciNet is in a sense a very rich network. So we have to check the downgrade of bandwidth interferability.
Thank you. So Jennifer has a question. So Jennifer, could you unmute and speak question?
Sure. I was just wondering if you could speak to the science drivers that are motivating this build out of your system.
Yeah. So one example is HPCI. So Fugaku generate a lot of traffic and communicate to the other organizations. So the request from the such members are rich bandwidth for transferring the data. Namely, Fugaku generate a lot of calculation data, and it should be shared by organizations. So its science project requires a lot of the bandwidth. Is this answer of your question?
Yes, thank you very much.
So audience, another question? Okay, thank you, Akashi-san. So we've had after the April this year, so the JP USA connection is also upgraded to 200 gigabps. So
yes.
We hope that more scientific collaboration will be enhanced by the use of SciNet 6. Thank you.
Thank you.
Okay, let's move to the next presentation, the final presentation of this session by Yves Oppe from Asia National Supercomputing Center, Singapore.
Okay, thank you.
Talk is evolution of Asia Pacific subsea cable capacity.
Okay, please allow me to share my screen.
Yes. It's editorial mode of, yes, good. Please start.
Thank you very much. Good evening, good morning, and good afternoon. My traditional little presentation on the evolution of the Asia Pacific subsea cable capacity, and also having a look beyond at what's happening in the rest of the world. So again, if we look at our global research and education network as exists today, it's quite impressive. Again, this is a subset. I noticed a couple of links are already missing. That's the GNAG map. And we have to remember that it all started in 2013 with the first demo between the US and the Netherlands. That was for the Tirina 2013. And the rest is history. On the Pacific side, the first serious demo was between Singapore and New Orleans for a supercomputing 2014. And again, the rest is history. And now we have about a terabit worth on both oceans. So this is a good sign. And as we've just heard from Akashi-san, new capacity is being added practically every day. Well, every day would be exaggerated, but every quarter. Now, if we look at what's noteworthy over the last 6 months, I think there have not been any significant additions on the 100 gig level. I think it's relatively stable, and we are all absorbing the capacity which we have been installing. The focus, I think, has been on 400 gig implementation. And again, we have seen the impressive work of SciNet 6 in Japan, where basically the whole backbone graduated to 400 gig in the meantime. And we see the same thing happening in ESNet, in Internet 2, in Canary in Canada, SurfNet in Europe, and et cetera, et cetera. Now, very interesting is we see coming the first 400 gig on the intercontinental level, at least on the Atlantic. And with the next cable in Australia, they have tested 400 gig, so we can foresee 400 gig on that side coming very soon also. Now, the 400 gig was first announced at the TIRENA meeting in Trieste earlier this year, and there again we have on the Atlantic 3 connections coming up next year. One is cross-shared between Canary of Canada and Internet 2, and the 2 other connections are ESNet, and the 3 will be on the new Amitié cable. So this, I think, is a very important evolution. As I said, on the Pacific side, we have to watch. I would not be surprised that within 2 or 3 years, we will also find 400 gig on the RNE side on the Pacific. 400 gig RNE ring around the world could be something. We thought 5 years ago that the 100 gig ring around the world would be far-fetched, but we have it today. We heard a lot about APOnet, and again, congratulations to Jennifer and to Francis and everyone involved. You really modeled very well what has been the case in the carrier domain where I came from. For quite a number of years, you have to provide mutual backup, mutual transit, and basically help each other, because facilities get broken every now and then, and unprotected facilities, as we all know in the meantime, are subject to failure. Of course, this creates and necessitates a lot of confidence and mutual trust, and also good tools to monitor and to repair. Arena Pack, we've heard that the Guam to Indonesia and the Guam to Philippine circuits will probably be coming next year. This is again very, very good news. One fiber and one new project which caught my attention is the Far North Fiber Express. In fact, there was a first project which was supposed to run on the Russian coast. That project was cancelled, and the new project goes through the Bering Strait and the Canadian North all the way to Europe, Finland, Norway, and now Ireland. So that will be very good and very interesting, because the Finnish side, the RNE will probably own a fiber pair courtesy of the government. So it will not be long before we see fiber capacity in the RNE community. Again, that cable is supposed to be ready by 2025-26. And just announced was an extension from that new cable to Iceland. And of course, Iceland is very important because they have a major industry of hosting computing and storage. And again, we all go where the energy is cheap and the cooling is easy to get, especially with global warming coming very soon. RNE cables to the South Pole. There has been an NSF discussions. The South Americans have been discussing the thing, and one of the big projects is the neutrino detector at the South Pole. So I think we will see these projects coming also. If we now look at the global subsea telecom, again, if you're interested in the subject, I would suggest you go to the submarine cable of telegeography. You'll find there 486 cables now. What's interesting is that it was thought that the current investment boom would slow down, but it's expected now to continue for at least another 2-3 years. And the major investors are the hyperscalers. It's not the telecom carriers anymore. It's really the hyperscalers, and it's really for their own use. And that's quite interesting. Now, the other interesting part to watch for us is that the number of these hyperscalers will start, and in fact have started, selling capacity. When I say selling capacity, this is not small capacity. If you're interested in a fiber pair, they are ready to talk to us. Now, here, noteworthy over the last 6 months is, first of all, the OAC cable, which will connect Oman to Australia. Very important cable, especially if one takes the SKA to account, the square kilometer array, which will necessitate a lot of capacity. Another one on this side of the ocean is the Topaz cable. That's a Google linking Canada to America, and RFS 2023. The Southern Cross cable is complete. Also very, very good news. And again, as I mentioned, they are testing 400 gig. On the Asian side, purely, there's the C2H2H, Hong Kong, Hainan, Singapore. The AAE1 has double capacity. Then the just announced the Juno cable, that's a brand new cable, which will connect Japan to the USA. NTT is the lead. We'll have 20 fiber pairs and 350 terabits of capacity. So this is not bad. And we can imagine some interest in eventually having a fiber pair from the R&E community between Asia and America. Then there's the EMC, which was just announced. That's Singapore, Middle East to France. And that's financed by Saudi Telecom. And again, very well financed. So we will see that cable coming through also. And that will basically help a lot on the Asia to Europe side, which is still a little bit feeble. So what happened to the Trans-Pacific cables, which we were supposed to see last year? There was PLCN, HKA, Jupiter, and B2BE. In fact, 3 of them got rezoned, redefined because of the geopolitical situation. And basically, you now have new routes for these cables. On the local side, a lot of activities still. We'll just go through them shortly. Southern Cross, we mentioned. There's the ECHO and Bitfrost cable, which will go from Singapore, Guam to the US. ECHO is Google. Bitfrost is by Keppel in Singapore. And again, will be quite a lot of capacity, also 12 fiber pairs. Again, ready in the next couple of years. Hawaii Kinui is big news. Hawaii Kinui was first supposed to go to Hong Kong, has been redefined to Singapore, and will also be ready in the next couple of years. And again, will cover Sydney and will connect into some of the other cables, obviously. There's the Google Topaz cable, which I mentioned. I like that cable because Port Alberni is a cable station where I used to go quite often in the old days. Now, another cable which is quite of interest is the Humboldt. Humboldt will link Australia to Chile. Again, very important on the southern hemisphere side, also important for SKA, and will connect into the future cable to the South Pole, and will also connect to North America, because obviously in Chile you have the Atacama telescopes, which are also connected in very high speed. That cable will also probably connect to Fermina, the new Google cable. On the Asian side, SGAC is coming, Asia Direct is coming, Royal Bengal Tiger is coming, C2H we were mentioning. There's the NTT MIST cable, that one should be ready next year. In fact, one hole in our 100 gig tapestry remains India. And again, it's also a matter of pricing there, but we can hope it will come down. There's the famous OAC cable, which I mentioned, and which now has also signed an agreement to connect from Oman all the way to Europe. Also very good news. There's the Singapore-India gateway, in still some reservations on the financing. There's the India East and West cables. There's the CMUE 6 cable, which has been delayed quite a number of times. Now it seems to be gathering steam. Again, 2025. There's the Peace cable. The Peace cable just announced that they completed the Pakistan to Egypt portion. They also decided and have the financing for a connection from the Peace cable to the Maldives and to Singapore. That would also be quite interesting, quite a lot of capacity. There's the Apricot cable, which is coming. Of course, we all remember what happened to Tonga, and obviously cables are vulnerable, and it's still a good thing to have some satellite backup if nothing else works. So I think we have been neglecting satellite a little bit as a RNA community, and it might be time to have a look again at it. There's, of course, the Google Global Network, which is a model network, and again, essentially for theirs. And basically, this was a lot of cables. As you can see, a lot will become ready in the next 2-3 years, and basically should help bring prices down, which should facilitate 400 gig in Asia, at least parts of Asia and over the Pacific. And then we will see new capacity. So that will conclude my presentation. It's a lot of material in a short presentation, but I just wanted to give you an overview, and the slides are on the website. So please consult them and send an email if you have any questions. And in the meantime, if you have any questions, please let me know. Thank you.
Thank you, Yves. Now, your presentation reminded us that this year is the 10th year when our community got 100 gigabps international connection. Yeah.
Yeah.
Do you have any questions to the audience? Yeah. I have no question, but yeah, thank you very much. Many informative update by this half year. So that I looked at half years ago, but this presentation includes more information, updated information. So the focus of SAS post is also included. Thank you very much for the presentation.
Thank you.
Any question? No? Okay, yeah, thank you very much. Now, Sato-san, do you have something?
I have an announcement for the correcting slides. Can you hear me? I have an announcement to correct some slides.
I don't understand what you're asking.
Yeah, because the hosting, we are collecting slides, and we are sending mail to all the speakers for this session. And if you not send it yet, so please send to the Senshi-san. And it will be uploaded to the regular website for the meeting. And we have also have the slide uploader, those who have the big slides. So those are the URLs for that. So please check your email box if you have any questions, or send a mail to the Sun-san. Okay, thank you.
Thank you, Sato-san.
Okay, understand.
Yeah, in this session, we share many information. So the internet to so the North America's infrastructure, and also Europe and Asia connection from USA, and also the Trans-Pacific and Oceania infrastructure, including JP APAN update. So we can learn more through this presenters information from now. Thank you very much for coming to this workshop. Next session will start in 40 minutes. See you later.
Thank you, everyone.